Welcome to the video on transformations. The purpose of this video is twofold. Number one, to review some basic transformations, and then number two, to talk in particular about one type of transformation known as the reflection. So what is it, first of all, a transformation? A transformation I'm thinking about is a mapping of some original figure called the pre-image. So the pre-image is going to be the original onto the image. I like to think about a transformation like I thought about functions in algebra class. So think about this like a function that takes a set of points, which is known as the pre-image, and applies a given rule, which is our transformation, and then outputs that set of points at a new location for the image. So for instance, in this picture here where we have the smiley face, this is our original or our inputs. Our transformation applies a given rule and outputs that original image or pre-image at a new location. Now hopefully you remember some rules from naming transformations from middle school. If I take this triangle ABC and I slide it across the page, then the outputs here are going to be, I'm going to call this one A prime, B will move to B prime, and C will be transformed or output to C prime. Some types of transformations that you've seen in the past and should be familiar with is a reflection. I think about a reflection as kind of a flip over a given line. So a reflection I think about as a reflip. A rotation I think about as a turn. And a translation I think about as a slide. A dilation I think about something that either keeps the same shape but either reduces or enlarges the size of the given or the pre-image. All right, down at the bottom it says label the following as a reflection, a rotation, a translation, or a dilation. And I'm going to have you go ahead, pause the video right now, and label each of the following. All right, number one, you should have notated as a rotation because it's a turn. Number two was a dilation because the size of the image got bigger. Number three was reflection because it was reflected across that purple line that I drew in the picture. And number four represented a translation because it represented the image sliding across the page. All right, I'm going to go ahead now and flip up to the top of the next page where we talk about a rigid motion or an isometry. A rigid motion, otherwise known as an isometry, is a transformation that preserves or keeps the same distance. You might think about this also as keeping the same size. So a transformation where size or distance remains the same. I could use the fancy word preserve. Now there are two different types of isometries that you need to be aware of and on top of this year. In a direct isometry, we keep the same orientation or order, and I'll talk a little bit about what this means in just a minute. An opposite isometry reverses the orientation or the order. So for instance, in this direct or in this picture of the direct isometry, they have this triangle which is named A, B, C. And in the naming of this triangle and going from A to B to C and then back to A, that orientation is in a counterclockwise fashion. If I look at the image, the new triangle, this red one, in naming the triangle A prime to B prime to C prime, notice that the orientation there is counterclockwise as well. So since the orientation in the original is counterclockwise and the orientation in the image is also counterclockwise, that means we kept the orientation, making this guy a direct isometry. Now in this one over on the right hand side that I'm going to circle with a green circle, if we look at the blue, which represents the pre-image, and we look at the orientation there, in naming this triangle ABC, the orientation starts out as counterclockwise. if we go and look at the image, this red triangle, and naming A prime to B prime, B prime to C prime, and C prime back to A prime, this orientation clockwise. And because the orientation has changed between the pre-image and the image, we call this guy an opposite isometry. So down at the middle of the page now, they're asking us to label each picture as either an opposite isometry, a direct isometry, or not an isometry at all. I'm going to be kind of a chicken and head right for number 2, because I noticed that in number 2, the sizes of these two guys are different. And because the size was not preserved, I know automatically he's not an isometry. And I just realized that in making your copies, I have some markings on yours that aren't on mine. So for this triangle here, I'm going to go ahead and put those hash marks in there. And in looking at these pieces here, A prime, B prime in the image is the same as AB was in the image. Those are marked the same and therefore are congruent. B prime to C prime is the same as B to C was in the pre-image. And A prime to C prime is the same as A to C was in the pre-image. So therefore, I know that this guy is an isometry. And now I need to make the decision as to whether he's opposite or direct. Well, if I look at the orientation in the original, looks to me like this guy is clockwise. Looks to me like this guy in the image is counterclockwise. So since those were reversed, this guy's going to be an opposite isometry. And now I'm going to go ahead and jump into number 3. And likewise, there were some markings on your copy that I did not put on mine that I should have. And the ghost is back in the computer again. All right, hopefully I've gotten rid of the ghost, but we will see. In going to look at number 3, the first thing I'm going to look for is to see if the pre-image is the same as the image. And in every case, they are marked the same. So I can go ahead and conclude that this guy is an isometry. And now in order to decide whether he's a direct isometry or an opposite isometry, I have to look at the orientation. So the orientation in the pre-image is counterclockwise. The orientation in the image is also counterclockwise. Since they're the same orientation, I can conclude that this guy is a direct isometry. Okay, down at the bottom, they want you to draw an example of each of the following. I'm going to let you go ahead and do that on your paper, and we'll take a look at these when you come back to class and see whether or how you did with them. In the meantime, I'm going to go ahead and flip up to the top of the next page, and we're going to talk about line reflections. I think about a line reflection as a transformation that will flip an object over that line of reflection. Think about looking at your reflection in the mirror. If you're wearing a shirt that has any kind of lettering on it, and you look in the mirror, the lettering is always backwards. Same size, but backwards. That makes a line reflection an example of an opposite isometry. So it'll change the direction into the opposite direction. So the orientation, the figure space in an opposite direction, that's what makes it an opposite isometry. Some good things to know is that the distance from a point in the pre-image to the line of reflection is always going to be the same as the distance from the corresponding point of that image to the line of reflection. If a point is on the line of reflection, then that point of the pre-image is the same as the point of the image. And we'll talk a little bit more about what that means as we work through these examples. So a reflection in the x-axis, I'll take all points and flip them across the x-axis. Notation that we're going to be looking at, we're going to use a small r to represent line reflection. That line that we're reflecting off over is going to go in subscript after that small r. So for this guy, Small r tells us line reflection. Y-axis tells us what line we're reflecting across. To reflect across the line y equals x, again, that small r stands for line reflection. The y equals x tells us that the line we're reflecting over is the line y equals x. And to reflect in the line y equals negative x, we're going to do almost that same thing, and I'm going to talk more about this on the next page where we actually take a look at some examples of this. But again, what it's important for you to know right now is that small r means line reflection. The line that immediately follows is the line that we're reflecting across or over. All right, so we're going to go ahead and take a look at some examples right now. Down at the bottom of the page, it says reflect point A with coordinates 3, -5 over the line whose equation is y equals 3. So the first thing that I'm going to do is I'm going to go ahead and I'm going to plot that point A with coordinates 3, -5. So point A is right there. We want to reflect that over the line whose equation is y equals 3. So the first thing I'm going to do after I plot the point is I'm going to go draw the line y equals 3 on my paper. So I want to take this point A and I want to reflect it across or over the line whose equation is y equals 3. Well, I'm not going to do anything more sophisticated or fancy than counting. I'm going to count the number of units between A and the line y equals 3. So point A is exactly 8 units away from line y equals 3. Its image is going to be the same distance away, but on the opposite side of the line. So point A was 8 units beneath the line y equals 3. Its image is therefore going to be 8 units above. So A prime is going to be up here, and he's going to have coordinates 3, 11. So in order to solve that problem, you essentially have to be able to do 3 things. You have to be able to plot point A, you have to be able to draw the line y equals 3, and you have to understand that the pre-image A and the image A prime are going to be the same distance away, but on opposite sides of that line. The next one says to take point B with coordinates -2, 5. So the first thing I'm going to do is go plot point B, and I want to reflect this in the line whose equation is x equals -5. So again, I'm going to go ahead and I'm going to draw that line whose equation is x equals -5. So there's x equals -5. And then I'm simply going to count. If B is 3 units to the right of this line, its image is going to be 3 units to the left. So I'll plot point B prime right there. Then I'll go find his coordinates. It looks like his coordinates are -8, 5. All right, let's go ahead and head up to the top of the next page, and we're just going to go ahead and do one of these one after the other, and we'll see what happens. In part A, they ask us to find the image of the point with coordinate 6, -5 after a reflection in the x-axis. They might have also written this as reflection x-axis, and you would have to know that these two in the green circles mean exactly the same thing. But I'm going to go ahead and plot that point 6, -5. So I want to first of all reflect or count the number of units to the x-axis. That point P is 5 units beneath the x-axis. So its image, P prime, is going to be 5 units above it. So its coordinates are going to have, or P prime will have coordinates 6, 5. Letter B, they want me to take the point S with coordinates 5, 8. So the first thing I'm going to do is plot that one. And they want me to reflect it across the y-axis. So I'm simply going to count. S is 5 units to the right of the y-axis. Its image will be 5 units to the left of the to the y-axis. So the new coordinates of S prime, -5, 8. And an interesting thing to note here is that when we reflected across the x-axis, the x coordinate stayed the same, the y changed to its opposite. When we reflect across the y-axis, the y coordinate stayed the same, and we took the opposite of x. Part C, I'm going to skip for right now, and I'm going to go ahead and take a look at part D. It says, find the image of line segment DC with endpoint D at coordinates 3, 5, and endpoint C at coordinates 8, 1, after a reflection in the line y equals x. Remember that this small r tells you reflection. This equation tells you the line. Well, unlike the others that were easier to do by counting, I'm going to think about what the line y equals x really means. This says y is equal to x and x is equal to y. So these guys here, it's going to be much easier to find their coordinates by just doing what it says to do in the equation. And this says the y value is equal to the x and the x value is equal to the y. So all I do is flip them. So C prime is going to have coordinates 1, 8. And I can go and graph that line y equals x. And the reason I don't do them like I do the originals is because the counting thing is going to be much more difficult with the slanted line than it is with a horizontal or a vertical. So for that one, I think it's easier just to remember the rule. The y is equal to the x is equal to the y. Part C is kind of the same way, but our rule is going to be a little bit different. This says that our y is equal to the opposite of x. And if I solve this equation for x, what I find out is that the x is equal to the opposite of y. I don't know why it doesn't want to let me write that on there. So if I follow that rule, our A prime, if I switch the y and the x and take their opposites, after a reflection in the line y equals -x, A prime will have coordinates 4, 2. B prime, again, I'm going to flip and take opposites, has coordinates 9, 2. C prime, flip and take opposites, has coordinates 9, 6. All right, and I guess we're going to call it a day for that one. As always, if you have questions about any of these, feel free to jot them down in the margins, send me an email. Make sure you make a note of it somewhere, though, so that you can remember to ask the next time you come back to class. As always, thank you for the gift of your time. Hopefully, if you learned something or reviewed something or we've done something meaningful and you've increased your knowledge by a little bit and it made that time worthwhile.